Hello, and welcome to Construction Tech, presented by House Accelerator, a catalyst of zero carbon building. We're happy you're here. We welcome all comers to our exploration of how to slash the greenhouse gas emissions of our buildings and make them more resilient to the extreme temperatures, wild weather, and grid insecurity caused by climate change. With our co-hosts, Kevin Brennan, Shannon Pendleton, Sean St. Amour, and Mark Willey, we produce this weekly series to dive into the details of Passive House construction practice, with a technical focus on technique and technology in the field. New to all of this, please visit the Passive House 101 section of our website to get started. With that, please enjoy Construction Tech and pose your questions in chat for the discussion session following the presentation. Thank you. All right, welcome everyone to the last Construction Tech of 2021. We're really excited that you're here and super happy to have Direct Energy Partners here to talk about accelerating the adoption of DC Microgrids. So with that, I'd like to hand it off to the co-hosts.
Thanks, Zach. I'm Kevin Brennan from Brennan Insulation and Airtightness. I am happy to be on the final episode here of Tech Tuesday. We're here in New York City. I think it's quite fitting that we're ending this year off with quite a few solar and DC options, because that's what happens in a passive house, is that you got to tweak the final parts. You know, you got to make the last bit work. So let's sit on the edge of our seats, and I'll kick it off to my friend Sean.
Well, hey everybody, look at us.
Live
hanging
show.
out.
Coming to you live from Brooklyn. Hey!
Hey everybody, I'm Sean St. Amour, hanging out at 475's head office while we're doing a bunch of work, and I was able to convince good old buddy Kevin to drop by his usual hangout, but it was nice to actually hang out with him in his usual hangout. So looking forward to a great show. Shannon, over to you.
Thanks, Kevin. Thanks, Sean. I wish I was in New York. I want you to take a run around the ice rink for me while you're there. And thank you, Zach, for leading us in tonight. Thank you to everyone for joining us. It's amazing that the year has gone by so quickly, and we're thrilled that you're here to share tonight's presentation with us. And hopefully you can stick around during the after hour for the Q&A. Put your questions in the chat while we put the presentation on, and get ready to meet two of the most amazingly talented and brilliant people that we've had on all year, Dusan and Giel. They are from Direct Energy Partners. I first saw Dusan at FIASCon doing a microgrid case study panel with Lisa White and David Peabody. And then he disappeared because he had a new baby. So please congratulate Dusan in the chat. He probably hasn't slept since FIASCon, but we'll enjoy learning the difference tonight between potential and reality. And we're going to see these guys do something that Elon Musk hasn't even done yet. They're at 98% efficiency, and they go through from a utility DC to DC with no inverters or converters. Their path to generator, inverter, transformer to end, they're saving more than 50% of their energy. So they're generating and consuming locally. So get ready to create a market for some open format DC microgrids, and say hello to Dusan and Giel. Thank you for joining us, guys. Welcome.
Yeah, thank you for having us, and thank you for the kind introductions. We're happy to be here.
Absolutely. I'm going to throw some links into the chat so everyone can connect with you on LinkedIn and learn more about you on the web while they learn more about you during the presentation. Go ahead and take it away.
Wonderful. Well, thank you for the nice introduction, Shannon. I hope you all can hear us properly. So also thank you to the audience for joining us today, because actually both Dusan and I are very excited to be here, and we will take you on a journey towards direct current microgrids, as you already put it correctly. Actually, what we will do is we'll zoom into the electrical infrastructure of our communities or buildings and we'll try to confront you with a kind of less obvious fact. And the fact that we're going to show is actually that the current alternating current way of distributing electricity is actually no longer compatible with the technologies that we're introducing into our energy system, that we're introducing into our passive houses, like battery storage, like solar PV for generation, but also all these efficient loads in there, heat pumps, air conditioning systems, you name it. I challenge you during the presentation to find loads in your house that are not supplied by DC or using DC in an intermediate stage, basically. In our presentation, so we'll first have a more kind of why section. So we'll explain you how we're distributing electricity today, how that evolved throughout history, and explain why we ended up in the current situation. And then we'll show you actually how things can be done differently and what are the advantages of having a DC microgrid instead of an AC electrical distribution. And then the second part of the presentation, Dusan will take you actually to our DC microgrid lab facility where he's sitting right now, and show you in practice how this technology is actually already proving to be beneficial today. So let's get started with the motivation, the underlying rationale for DC systems as such. Why DC microgrids? I'm going to take you back to the future. Let's get back to the early days of electrical power systems in New York, Pearl Street, but all over the world. End of 19th century, 1880, 1890, we saw a gradual uptake of electrical lighting in streets all over the world. Those were very basic electrical systems. You should imagine like maybe a couple of hundred light bulbs that are connected to a single generator station. And Thomas Edison obviously was one of the pioneers of light bulbs, but he had one major drawback, and that actually there was no electrical infrastructure at all to power them. So at a certain point, he decided on his own to start developing electrical power distribution. He built his own generating station in Pearl Street, New York, and he started distributing power to basically light up all the houses in there. Small scale systems, think about order of magnitude 100 kilowatts as such. And this happened basically all over the world. Also where I'm living in Belgium, basically same trends appeared, same type of technology was being introduced everywhere, basically. Always small scale systems with a relatively minor amount of consumers connected to it. And these first systems, it may not surprise you, but actually they opted for direct currents to transmit power. Direct current meaning actually that the voltage that you measure at the socket outlet is actually just a constant. It's just continuously one line, one flat line over time. And that differs from alternating current, what you would measure if you would put a probe into the socket today. An alternating current that actually jumps up and down at 60 hertz, going positive, going negative all the time. Now, why did we end up with alternating current today? Why is that still the mainstream technology? Well, that's explained by the fact that DC was relatively limited in the range you could cover. You could cover about 1 mile with a DC distribution line. That was it. Did that stop DC from being introduced into cities? No, they just resolved that by putting a lot of electrical power stations into our cities, which were dirty, causing troubles with air quality as such. So it was not the preferred way, but anyway, it was the only way to light up the cities and to power the motors in there. But then we arrived in the 1930s, and actually then large investments in infrastructure were made following the economic crisis of 29. And basically government policy ordered a lot of infrastructure upgrades, also bringing power to remote communities all over the US and the world. And there we got stuck with the range issue, basically. And that's where AC came to the foreplay. Basically, AC allowed you to step up the voltage towards higher voltages, distributed over miles and miles of distance, and locally bring that voltage back down to a level that you can use to power your lighting, your motors. So that's the model that was being introduced 1930s, 1940s, primarily because government supported it. And that led to a massive wave of electrification all over the world. Generating power centrally, distributing it over long distances, bringing it back down to an end-use voltage level, and then bringing it to end users as such. That's the model we have today.
And Giel, not to know, but just to add to it a little bit, back then it wasn't so easy to generate high voltages with DC due to the lack of power electronics. But in order to generate high voltage AC, you just need an iron core and wrap some copper windings around that. And depending on the number of windings you have your voltage and can transmit power over distances. So it was also very, very cheap to do the voltage transformation, which allowed you to transmit power over distances.
Exactly. So some may say the transformer was the missing technology, or the DC transformer, if I don't violate the law of physics there. I do, actually. Was actually the missing piece of technology that Edison lacked to make DC mainstream. Yeah, that's for sure. Now times have changed since then, obviously. Back then it was used to power lighting, it was used to power some motors in there, but that was basically it. We all are witness of the fact that today the range of applications that require electricity has expanded significantly over the laptops that we're currently looking at and talking to, over our LED lights powering our spaces, but as well on the generation side. Electricity is more and more being favored. And I liked actually in the introduction that also electrify everything was mentioned in there. And that's actually what we're doing for sure. Also for heating, ventilation, air conditioning, those systems sitting on rooftops, they are typically electric nowadays. And this trend will further continue with the electrification of transport, with more and more battery storage being added to the system, potentially fuel cells. I mean, you can put a lot of slides talking about applications requiring electricity, and that's almost one of the only certain facts in life that our future will be increasingly relying upon that energy carrier, basically. You then look under the hood of all these applications. Actually, the majority of them operates on DC power. So the symbols reflecting the alternating nature of the current and the direct nature of the current. In the early days, lighting didn't really care. You can power a light bulb with DC, with AC, it will light up. Motors, it was preferably AC back then, because you had way less maintenance with them. DC motors were more maintenance intensive because you had like small collectors sitting in there that generated sparking and wear and tear on the devices. So their AC was actually a preferred technology nowadays still. However, if we look into electronics, if we look into LEDs, solar generations, especially all applications where we use semiconductors in between, their DC is actually the nature of the current that these appliances require. Electric vehicles, the same thing. Battery storage, the same thing. Fuel cells. It's all direct current as such. heating, ventilation, air conditioning is because it has drives that most motors in there. Again, their AC is the preferred option. However, that AC differs from the AC that you get at your socket level. So it's not a 60 hertz AC you typically send into an HVAC system, neither to modern industrial drive systems and motors. It's actually an alternating current of a different voltage and frequency that you get out of the socket. That's why for all these applications, we put in power electronics in between. You can call them adapters, you can call them inverters for solar. And actually what all these power electronic converters, as we commonly refer to them to, what they all do is converting DC into AC and the other way around. So the future is electric. The future is more and more relying upon power electronics. Now, going back to the first part of the story, our future is also becoming more and more decentralized. So we're also going back to that initial picture of having a lot of decentralized power generators into our systems, now being renewable generation in the system. So no longer coal-fired based small-scale generators, but renewable generators, but they are decentralized. And that makes a lot of sense because a solar panel that you put at the utility scale PV plant of multi-megawatt systems, that's exactly the same technology as you put onto your roof. So basically economies of scale and efficiency benefits no longer play in this world of renewable power generation. So that's why it makes more sense to co-locate our generators, our PV modules, with the loads in there and try to keep the distance between generation and load short as possible and save a lot on the infrastructure and the energy losses that happen in between. The system is also becoming more modular. So we're using PV modules, we're using power electronic modules. So that's making it also more reliable in a way that no longer there's like a single large scale central power station that presents us with a single point of failure. However, managing all these energy flows onto our system, that will present a significant challenge ahead of us. So it's not just a handful of generators that need to be synchronized and controlled. It will be millions of them, basically. And that's where microgrids come in the story. So we're talking about DC, but we're talking also about DC microgrids. And we at Direct Energy Partners, we are strong believers of microgrids because they allow a kind of divide and conquer approach. So imagine having all those millions of generators, loads, all exchanging energy one with another. How are you going to manage this entire system? Well, by subdividing that large part of generators and loads into smaller scale microgrids, actually you can actually manage all these power flows in a more proper manner. What is a microgrid? It's basically a set of generators, loads, and storage systems that form an entity, that form a system altogether. And they can exchange power with neighboring microgrids, but they also achieve a certain level of independence. They can operate standalone if that would be economically the best option to do, or just technically necessary. For instance, if there are a lot like power disruptions following natural disasters, or utilities just causing preventive blackouts in there. Dusan, feel free to jump in if you have some thoughts.
Yeah, no, this is good.
Otherwise, I'll just continue.
I'm excited to get to the real world scenarios, talk about the projects and how we really accelerate the adoption of these systems. But this is good. The power electronics based future. I particularly like this slide, and you will talk about it in detail because it will show you really how much you're really wasting between just in a in capital equipment, just converting AC to DC. I think it's typically not apparent to people. So I'll let you take it from here.
Yeah, exactly. We're often confronted with questions like, okay, but if we're gonna convert to DC, isn't that like having a lot of repercussions on these adapters that we're already using today? And actually, if you open these things up, and we frequently do that as hands-on power electronics engineers, you typically recognize a very dedicated part towards rectification, converting AC into DC, and a part then converting that DC into a lower or higher DC voltage, depending on the application. Your laptop adapter typically looks like this. So there's this red part for rectification and this yellow part for voltage control in there. The same applies for solar inverters. Then we're looking, of course, at a larger unit as such, but again, we have a DC-DC stage taking in the solar power, and then a DC-AC stage to invert that and make it compatible with the voltage that our utility provides today. So DC results in a lot of simplification, because actually our current system looks like this. If you break it down into blocks, although this may be like single units hanging in your garage or sitting somewhere, internally they consist of two major parts. And it's pretty obvious that by actually moving towards a DC infrastructure where we move that AC stage as much as possible up front, we can save on material in between. We can save on electronics in between. And those savings...
Let's make this a little more interactive. So can you go back to the previous slide? Sitting here in the lab, I'll do a little plug for LumenCache too. I see Derek joined. So this is a lighting driver that's been taken out of a typical 2x4 fixture. And you can see the amount of electronics that are involved, and mainly they are there for converting AC to DC, doing some filtering and whatnot, just to power LEDs, which are natively DC. And this thing right here, which is a LumenCache DC-DC driver, is the equivalent DC-DC to run the exact same light on DC. I mean, if this doesn't convince you that DC is more efficient, I don't know what does. But we have many more examples like these, and so we can even improve the electronic waste that we generate by moving everything to DC and minimize that. All right.
Yeah. Exactly.
Just thought that was neat.
So minimizing electronic waste, but also just lowering costs. You have less parts in there, so it costs less upfront. But also, if there are less parts where the current needs to go through, you have less losses in that entire chain. So the better compatibility between DC infrastructure and the devices that are connected to it yields a lot of benefits in terms of efficiency, in terms of material resource savings, but also reliability improvement, less components that may fail in between. Besides savings on these power converters, which is typically the main driver for DC microgrids, the same cable infrastructure can be used to transfer more power as compared to AC. Side note, it depends on the voltage and stuff, so you need to do some math to prove that. But typically for a similar order of magnitude in voltage as with AC, we can transfer about 40% more power across the same wiring infrastructure. And that perfectly fits with our increased level of electrification. I wonder, is this already applied somewhere? Are there real applications out there in the field using it? And for sure there are. Dusan is sitting in our lab currently where we're working on it. But actually this DC trend started or got its like renaissance about 15 years ago. And that started off with the data center industry. The large digital players in the world building data centers, multi-megawatt facilities, 5 years ago, I was talking these were like 5 megawatt facilities. Today, these are 40 megawatt facilities. They consume for about every square feet approximately the same as a typical household would do. And you have like a lot of server infrastructure there, IT, electronics. So it's quite obvious that by distributing DC power in there instead of AC, you save a lot of electronics in these systems. You reduce the footprint. There are examples out there proving that you can save about 1/3 of the overall floor space in there, but also you generate less heat. Those megawatts of electrical power that go in there basically get out there as heat. It needs to be cooled. So there is also in a second stage savings in the cooling system overall. So these were the first adopters of DC, we can say. Secondly, there are commercial buildings and districts where you typically find combinations of solar, storage, EV charging infrastructure in there. Again, same motivation, efficiency, benefits, and converter savings. It continues in industry. So within industrial manufacturing plants, and especially here in Europe, there are a couple of pilot projects ongoing right now where part of the industrial production lines get powered on DC. Why do they opt for DC technology in there? It's because actually they are willing to improve the uptime of their manufacturing lines. That means that they are starting to introduce battery storage in the production lines. Where you find battery storage, where you find like motor drives for all these servo machines driving the robotics, driving the conveyor belts, you save again on material in the system. So it's basically the trend towards an increased uptime, improved power quality that's pushing the industrial manufacturers towards DC technology. For street lighting, there are a variety of pilot projects out there. Of course, on the LED driver, as is already perfectly demonstrated by the fact that you can reduce the size almost by a factor of 10, as Dusan already showed you. Within street lighting, there's another additional benefit, and that's basically you can connect more lights and you can cover longer distances as compared to AC. And that's because now we can increase DC voltages because we have these power electronics now. So the DC transformer, as we already talked about, now is basically a need that has been fulfilled by power electronics that were introduced late 1960s. Also, an application that's close to our heart is remote rural electrification, because there's still, now the number dropped, but we are still near 1 billion people worldwide not having access to electricity because there's no electrical infrastructure being deployed. And there you see solar home systems popping up, small kits that these people can purchase for a couple $100s, and they get electrical power. And it's obvious these things just operate at DC because it's evident to choose for it. Why go through the hassle of building it in AC? And then there are non-fixed applications, mobile applications on board aircraft, on board ships. In there, in aircraft, for instance, one of the major drivers towards DC is actually weight reduction. So a lot of the hydraulics in there are being replaced by electrical actuators operating flaps to fly the aircraft. And those as well require converters in there. And those converters can be smaller. You save on weight as such. So the advantages, benefits are actually very obvious, but we unfrequently recognize them because we're so much used to AC as such today. DC Microgrids Worldwide, we map them. We keep track of the pilot projects that are out there worldwide. So we have about 80 currently on the map. If your area, or there's something in your area ongoing that's not yet on the map, feel free to reach out to us and we'll make sure that a pin gets dropped. But I also invite you all to make sure that actually your area gets covered in there as well. So in a couple of years, we definitely hope that actually we can no longer keep track of this number of DC microgrids worldwide, because that would actually mean that the technology has eventually made it to a mainstream technology for power distribution. But for now, we still keep track, so send us yours and we'll add it in there. It's freely available and public on the internet, so go and take a look for sure. And with that being said, I'll hand it over to Dusan, and we'll gradually get to our lab tour in there.
Okay, sounds good. Thanks for that great overview. So Giel brought us to the 21st century and showcased everybody why DC makes sense today. So hopefully we're all on the same page. With this slide, I'd like to showcase some of the real world projects that we are working on to bring flagship DC microgrid projects to the market. When we started this business, Giel and I, we thought we were starting a business, but it turns out we're starting a market too. We still live in an AC world. Well, we live in a DC world with an AC infrastructure, and there are still a few challenges when you deploy these DC microgrids, but nothing that we can't overcome. So from the top left corner, I think this is one of the most ambitious and exciting projects we have going on in Hawaii that's in design currently. This is called the Ridges at Olomana Heights, and it's a community of luxury homes. And this entire community is being self-sustained from a direct current microgrid. So the generation is solar as DC and energy storage, and we have some hydrogen fuel cells there as well. And we have a central power plant that's distributing power to each home as DC. And then locally, we also consume as much power as DC as possible. And for some of the legacy loads that still require AC power, we just locally generate AC. There are a lot of challenges in designing something like this. So we're always looking for partners and companies that can help us overcome those challenges. But I'd say primarily it's mainly about how do you actually distribute power within the home as DC, right? We know how to distribute the power within the community. But once you get inside the home, things can get a little bit tricky. And so in this particular design, because everybody is on the same DC microgrid infrastructure, this community is not only self-sufficient, but it's also resilient. Homes can actually share power within with each other if they need it to help them weather any kind of adverse weather conditions. The picture in the middle, this is the project that we worked on with David Peabody up in Maryland, and we were involved in the design phase of this project. And up in Maryland, they are also deploying 6 homes and connecting them with a DC microgrid. I don't think this particular community goes as far as consuming power within the home as DC, but the distribution network behind the meter is definitely DC. That one has its own challenges because it was in a regulated utility. And in a regulated utility, you can't share power across property lines. So it's more of a regulatory issue rather than a technical issue. We have a couple more projects I'm just going to highlight here. We're designing an apartment complex in Hawaii as well. So the picture on the bottom middle, that's a 34-unit apartment complex. And it's pure DC. We have a parking garage that's wrapped in building integrated solar, and we generate enough power to meet the loads of the building and to charge batteries. So really, there is a single point of connection to the utility, but the utility is used as a backup. And I think that's true with every DC system that we design. We still put one connection to the utility there, but it's only used as a backup for these particular projects. And so here we generate power as DC, we distribute it as DC, and we consume it as DC. So this building has its own power plant in a basement, if you will. And then all the power gets distributed between the floors as DC and goes to the apartments as DC. There are still some, like, with that one, there's still some legacy codes in our national electric code that prevent us to build a pure DC building, if you will. For example, the National Electric Code requires you to have AC sockets every 6 feet or so. I'm not sure why a standard picks a technology as an AC socket, but I think over time that's going to change. So for now, we still have to put in some AC sockets just because it's required. We're not going to die on that hill, but we do see that it's going to change over time. So and then Giel has a couple of projects in Belgium. So do you want to talk about that one?
Yeah, just briefly, indeed. One of the main projects in Belgium that we're having here is in the lower right corner. That's an industrial site, greenfield, basically. It's currently being developed, and there actually we're going to build a DC infrastructure to basically distribute power and primarily share power between office buildings on there. So there are about 20 buildings planned there. And we're currently realizing the first blueprint of one of the office buildings that will then be replicated across the entire site. And what's unique to this project is the level of electrification and the level of autonomy that this site will have as compared to similar sites out there that typically source their power externally. So here really the goal is to share power and to generate nearly 100% of the energy on site. And then on the upper right corner, that's actually more kind of luxury project that we're doing. That's basically a new IT company, or an IT company, an existing one, that's building a new office building with also some living areas in there. And there the goal of the developer is really to introduce a lot of innovative technologies. So he took us by the hand to basically design the electrical infrastructure for that. And basically for us, that's an opportunity to also showcase and test basically some real new DC applications that haven't been used into the other projects before we put them into practice. Now, one more thing I want to highlight is actually about the autonomy, about the capability of these DC systems to operate in islanding mode and work standalone. I don't know how many of you have gone through the hassle of making an AC microgrid capable of transferring from grid connected to islanding mode. Although in theory, it's perfectly possible to go from grid connected to islanding mode with transfer switches, it requires a lot of hardware switching in between. It never gets done simultaneously. There's always a very brief, though a millisecond interruption. You will notice it into the voltage. In DC, transferring from grid connected to islanding mode is straightforward, easy to accomplish. You don't need additional hardware to accomplish it because you already have inverters sitting in there anyway. So it's merely a set point. That's basically it. I'm now going to hand it over back to you, Dusan.
All right, I think this is a good. I don't know how much time we have, Shannon, but I'd like to talk about the lab a little bit.
You've got some time, Dusan. Go ahead.
All right, sounds good. So I think it's a pretty good segue to kind of showcase what we're working on here. A lot of these projects that we are designing also require a lot of R&D on our part to either convince manufacturers to provide some of the products to these projects, or for us to develop new control systems and strategies or products that are just not available yet. So I'm just kind of gonna do this live. I don't know how it's gonna work, but let's go with it. So we're in our DC microgrid lab here. We have 34 kilowatts of solar on the roof.
Sorry to interrupt,
And then,
Dusan.
yeah.
Gil, could you stop sharing your screen? I think we'll be able to see Dusan.
Yeah. Perfect.
Thank you.
Okay. And everything in this lab pretty much runs on DC. So these high bay lights behind me, they run on high voltage DC. These big ass fans, they run on DC. They're all directly connected to solar. We have a electric car, and I'll talk about it in a little bit, that's connected to the same DC network. Appliances from LG, washers, dryers, stylers, TV that are connected to the same DC distribution network. You might ask, well, how do you distribute this throughout the building? Well, we had to design what's called a power distribution panel. And I think Giel was talking about islanding. And yes, it's possible to island AC microgrids with equipment, transfer switches and isolation equipment. But this single power distribution panel, that's the exact same size as your typical lighting panel that you have inside a commercial building. These are just circuit breakers. This also takes solar directly in, it takes batteries and power from a bidirectional converter. So when you're actually switching your loads on and off inside the building, your lights and fans or EV chargers, they're no longer powered from a single source of energy, they're powered from 3 sources of energy. And if one goes, then the other one fills in the voided energy. But because everything is on the same power type DC, this is the only equipment you need. If you ever try to buy a Tesla Powerwall, for example, they sell you the Powerwall, but in order to make it island, you need to buy 25 or 30% more equipment, which will take up space on your wall as well. But with DC, everything kind of integrates really nicely. So that's kind of what some of the equipment looks like that we have to develop because the market doesn't have it. If it was the daytime, you would see that we are charging now this is an Audi e-tron. Last week we had a Tesla here too. But we're working on the charging controls to charge these directly from solar. So solar doesn't go through an actual converter. It comes here directly to the charger, and then from the charger goes directly to the car. And so there's just something about converting those photons and taking that energy directly into your car. And this is what I told Shannon, that not even Elon Musk is doing this today. But that's because we still live in an AC world, and we don't have a DC distribution network that you can plug these DC chargers into. I guess let me show one more notable thing here in the lab. These are what's called high voltage DC plugs or DC sockets, and they can carry a lot of energy, up to 5 kilowatts or so. And so at home, you have your 240 AC sockets that look different than your 120 AC. Well, this is what a DC socket looks like. It's a company called Anderson Power that makes the sockets, but the plates and everything, we kind of have to productize and make it our own and put it into these projects because nobody sells these yet. And so with DC, you're always, people ask, well, what do you do about arc flashes? Because DC doesn't extinguish its arc on its own. Well, these little connectors are kind of designed in a way that they extinguish the arc before it even reaches the end user out there. So I'd say those are like the most notable things here that we are working on. And so we're working on DC safety and DC control systems. And I'm not sure what the next presentation slide was going to be, but as you can understand, it's very cumbersome or difficult to deploy these systems today. We realized very early on in forming our company that we don't stand any chance of accelerating the adoption of the DC systems if we don't do anything about the high cost of engineering and the high cost of barrier to entry of adopting these DC systems. What Giel and I have been working on for the last 18 months or so is we've designed a software tool which allows us to deploy these DC systems much quicker and much easier. It kind of takes all the engineering around making sure that components work together, so interoperability, making sure that systems are stable, making sure that systems are safe. It kind of takes it into the background and literally reduces the time to design these systems by more than a factor of 10, if you will. So that's kind of our effort of trying to figure out, well, how do we actually make sure that more people can get access to these systems? And so we want to make sure that the design and engineering is easy, as well as the deployment of controls and commissioning of these systems as well. Giel, do you want to add something to it?
Yes, exactly. I mean, we started developing this in-house because we really had an emerging need. I mean, we needed to become more productive because more and more projects were coming our way, and we're of course very happy that we're involved in a lot of these initiatives and that people reach out to us. That's definitely a sign that DC is taking off. But at the same time, it confronts us with our own constraints and limitations. So just like architecting these systems, actually by having now just a very simple tool to draw everything, we could already like save indeed about I'd say that you can now draw your system in, let's say, 10 minutes instead of like 2-3 hours that you would typically require. But besides, actually, I mean, while we started working on this, and first that started with the initial idea, actually we came across a lot of additional use cases as well. For instance, also to like centralize all the information, because like typically when we start working on a DC system, we in the early days, actually we maintain a lot of information in separate spreadsheets. We maintained some information in shared folders, data sheets, manuals, etc. And actually by the time when you went towards commissioning, actually a lot of information that you needed to get your system up and running was like distributed somewhere, sitting on any shared drive, somewhere in mailboxes. And that's also kind of a thing that we started working on, also try to gather all that information in a single place, where that once you're in the field, you can just go there with your iPad, you can consult product manuals, you can consult product specifications. And having that information in there also helps you to identify issues already in the design stage. Will that LED lighting driver work if my voltage drops to 320 volts starting from 380? Will actually the wire size be appropriate for what I need in here? Because that's also then an extension we started to build. We can simulate these systems. We can look at what the voltage would be in case this is the loading condition. We can look at what happens if there's a short circuit on our DC system. How quickly will the voltage drop? Did we put in the right protective devices? Did we put in a lot of capacitance? A lot of things that, a lot of questions that you as a design engineer are confronted with are actually tackled by means of this software tool. And that completely fits into our mission actually to accelerate the adoption of DC technology. And actually in our next step as a company is actually to release this tool chain to the outside world. We're currently in the process of onboarding partners. We already have a couple of them that started using a tool that was first developed for internal use. And that way we're trying to actually equip existing installation companies, system integrators with the expertise to design those DC systems without having to go through an entire study before. We really guide them through the process and provide them all with a kind of recipe of how to design and operate DC systems.
Yeah, so I'd say, you know, this tool is really good for assessing safety, stability, reliability, interoperability of components, and helps even develop the controls for these microgrids. We also found that to be something that's very expensive and it's lacking in the market as well. So yeah, there's some technical challenges and hurdles in implementing these microgrids, but I'd say most of the hurdles are around operation and maintenance of these larger systems. Technically, I think we can resolve how do we accelerate the design process and deployment process of the microgrids. But there's also the business end of things around operation and maintenance. And so we're always looking for partners who can help us realize these ambitious visions.
I think that's a great place to hold for just a moment and ask you guys, besides sharing all of your thoughts, all of the best practices, the costs, the design, and open sourcing it, where did you get your inspiration? I think I mentioned we might ask you about this. Do you have anyone who inspired you to get together and start this company and start driving this adoption forward?
Well, from my end, I actually started with this DC microgrid about back in 2012, I think. I was part of Bosch's management trainee program. And when I graduated from that program, kind of wanted to start my own company. And then Bosch, one of my old mentors, John Sassal, he asked me, he's like, hey, would you like to join a startup within a large company? And so the startup was actually to create DC microgrids. And I think that was the best thing I've ever done. So Bosch funded an internal startup for DC microgrids. And during that time, I think it lasted for about 5 years or so. And during that time, we deployed microgrids across the nation and even changed the national electrical codes. But at some point, Bosch kind of lost their patience and they got out of the business. And, that's when I had a decision to make, which was kind of a hard one, whether I take this really nice, 6-figure offer, move to Germany, do another startup, or do I start my own business and kind of fulfill the mission that we started? And so, well, here I am today. And so I think, 10 years into it and going strong.
Thank you, Dusan.
Yeah.
And Giel, what about you? We've got a couple minutes before I have to hand it off to Zach. You don't look like you have that long of a track record because you look very, very fresh out of school to me. So please abuse me of that. Tell me that you're a mid-centurier.
Well, actually, the story of Dusan and I mean, we definitely see some parallels in there. In my case, it started about in 2012. Back then, I was at university finalizing my engineering degree, and I happened to dive in one of the subjects in the list, and that was about getting to DC microgrids. It was my promoter back then who was also very much involved with Berkeley National Lab, etc. That pushed me actually towards this subject. And to me, that was more like a way to, before I graduate, let's just review how electrical power is distributed completely. By diving into DC, I actually have an opportunity to kind of go back to the basics and find out how electrical power distribution actually worked and review all the technology. And afterwards, I ended up doing a PhD degree with the same promoter in there. So I spent about four years at the university there. And actually, I'm very grateful that he gave me that opportunity, because actually, I was allowed to build actually the first DC microgrid of the 21st century in Belgium by the research funds that were provided back then. And that opened like a lot of doors then.
I can imagine. Yes, that is quite a first.
Exactly. And then at the end, I arrived at like these typical existential questions like, okay, you're near your PhD degree. Okay, what's happening next? Will you go for postdoc, whatever? And then I was just sitting together with my father in the southern part of France. And actually, I was already playing with the idea for a couple of years to like start an own company. There was an interest from industry. And I just then went ahead and one night I just said, okay, let's do this. Let's try this out. We have nothing to lose, and feels like the only way to kind of contribute towards accelerating the adoption worldwide. I ended up doing that, and then a couple of months later, Dusan and I partnered up and said, like, look, this is not going to work if we just tackle this on our own. We need to share insights. I mean, our vision of accelerating this and making this also a more open approach as to compared to what it has been before, it's very much aligned. And since then we're like partners in crime, I guess.
Mhm.
Partners in Acceleration is more like it, and I'm very glad the two of you met. I hope everyone can stick around to listen to the questions and answers during the Q&A portion after the presentation. And with that, we'll hand it off to Zach.
All right, thank you. So everything we do at the Accelerator comes thanks to generous support from our sponsors. So thank you to our founding sponsors, 475 High Performance Building Supply, Baxtingwe Architects, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification Units, Mitsubishi Electric Train HVAC US, Partel, RDH Building Science, Rockwell North America, Stocorp, and Zola Windows. Thank you also to our champion sponsors, Icon Windows and Doors and SIGA, and to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you too to our patron sponsors, Aero Aggregates, Aero Barrier, BR+A Consulting Engineers, Brennan Airtightness and Installation, Euroline Windows, Inotech Windows and Doors, Lamelux, Sanderson Sustainable Design, and US Engineered Wood T-Stud. So a big thank you to our supporters. On the Passive House podcast, the latest episode is an interview with my dear friend, Skylar Swinford, who is a Passive House consultant. He's a longtime committee member of the FIAS technical committee, highly sought after building science and Passive House expert. He talks about both his own project, his own single family FIAS Passive House project that he just completed in Boise, Idaho, as well as the relationship between Passive House and the acceleration of the clean energy transition, specifically the relationship between energy efficiency of Passive House and this movement to electrify everything. Super interesting insights from Skylar, so please check that out. We're also almost wrapped up with our bonus episodes from the FIASCon conference in Tarrytown, New York. The most recent is an interview with John Wolfling, who is with Datner Architects, and he talks about this massive FIAS affordable housing Passive House project in New York City. It's really cool project, and it's a fun and very short episode with John Wolfling. So check that out. Tomorrow, on the Global Passive House Showcase, we're wrapping up the 2021 showcases with a return visit by Satpal Kaur, who's going to be talking about this really awesome project. This is a reaching net zero on the sea. So if you can make out that that's a line drawing of the US or the SS United States ship, and she is involved in the retrofit, the upcoming retrofit of this ship to become a net zero project. So she shares some really interesting parallels between Passive House practice and the work that they're doing on this ship. A really innovative and interesting conversation or presentation that she'll be sharing. Finally, I've been looking for a chance to thank Derek Calburn from Lumencache for this cool surprise gift that we received. So when we were at FIASCon, I mentioned FIASCon in Tarrytown, Michael and I received a little package from Katrin Klingenberg, which was a surprise, a package from Derek. And he sent us these cool switches for low voltage systems by Lumencache that are branded with Passive House Accelerator. I don't know if you can see that. It says Passive House Accelerator there, and then the Lumencache logo. Anyway, that was really thoughtful and a fun gift. We have 4 of them, so I was thinking maybe it'd be fun to give one to each of the co-hosts of Construction Tech. So anyway, thanks, Derek. Thanks, everybody. See ya.
Excellent. Thank you, Zach. Oh, good. The guys are here. Come on in.
We are. So exciting. This has been a fantastic night. Derek, hey, thank you for joining us. It's always a pleasure. You're somewhere in China. We usually catch up on Wednesdays. But thank you for joining us tonight. Great stuff. Now, gentlemen, when we first came on talking about DC, I actually thought, there might have been a chance to have Batman and Superman on, but you know what? You guys are Batman and Superman. So great information, lots of good stuff. For some people, though, that do need to depart, I get it. If you want to stick around, there is a plethora of questions that we need to get into. So we'll get that in a second. But if you do need to go, from all of us on the Accelerator, from the Tuesday night show, enjoy your holidays. We wish you and your family a relaxing few weeks. Hopefully get a chance to rejoice with all the good things that have occurred this year. We're looking forward to another amazing year. So everyone here from the Accelerator, we say goodnight, say Happy New Year, Happy Holidays. Otherwise, we are going to get over to, what do we go to now, Kevin? We go to the overtime. And hey, he's wearing the jersey. The Chicago Blackhawks know about overtime, and that's what we're about to dive into. So if you got to leave, we'll see you soon. Otherwise, Shannon, dive into the queue.
Let's put these questions in the back of the net. All right, let's go.
Top
Great
shelf.
presentation, guys.
Far down.
How many sports metaphors can you fit in between Kevin and Sean? I'm not that many. You guys are pretty close over there. I'm loving this. I wish I was in New York with you. Maybe I can get in the car after the show. So we have a bunch of questions for you guys, and I have many of my own. But we are going to start off with one from Scott Kennedy. And Scott, when I invite you to unmute yourself, I know you had probably about 4. So why don't you start with one and we'll make our way back around, okay?
I'll start with the biggest one. And it's interesting to sit in this discussion because I have an off-grid cabin in an off-grid community. And we have a number of things we need to power. And we've been debating how to do it. And I've been urging to go to DC. But we do have AC pumps for our sewer system that we need to run. And we do have, fairly long 600 volt AC lines that run from our central big diesel generator out to where these pumps are. And we've been trying to figure out, how much energy are we going to need to do? How big a battery bank are we going to need to do? And can we go all DC? I've been urging us to go there, but I don't know about the availability of DC motors for pumps and those kinds of things. So we keep talking about converting this stuff up and down and up and down and up and down. So the issue for me is the availability of the equipment that would allow us to actually do this. And so I'm curious as to what you would say and what voltage would you recommend? 600 volts, higher volts, what kind of things would you think?
Yeah, I could take a stab at it quickly. So we also often run into these issues with manufacturers, and we're pushing them to provide what we call high efficiency pumps and high efficiency drives. Because if you can attach a variable frequency drive to it, you can make that conversion to run on a DC a lot easier, if you will. Of course, I always prefer to have DC motors. DC motors are just more efficient and they're smaller in size as well. But because we have to be kind of realistic, if they're not available on the market, the next best thing is to interface them with a variable frequency drive, if you will. And as far as the voltages goes, we typically like to use higher voltages for distribution of power over distances. So 700 volts DC or so for distribution. And then within the buildings, we step it down to 350 volts DC for the local distribution. And then depending on what end loads you have, you can have anywhere between from 48 or 24 volts DC. Giel, do you want to add something to it?
Yeah, exactly. Yeah, like the project that I showed of the industrial area, there also we plan to have like a central rainwater collection system. So there are also pumps involved there, and the challenge there for the larger pumps is it's not that complicated because there is already a variable speed drive in there because they want to run it at different speeds. So it's basically then tapping into the DC bus of that drive unit already in there, and those DC buses are even available. So there are connection terminals even in there already. Mm-hmm. So that's not a particular issue. We more run into issues like with the smaller pumps, talking about 1 kilowatt, 2 kilowatts that are just directly fed with AC power as such. And there, typically the only solution that remains is just to have like a local, in our case, 50 hertz AC conversion in there. But having it still supplied from the DC side. In a couple of projects, we also looked into the possibility of having like a parallel infrastructure where you're anyway having AC coming in from utility and DC. Maybe it makes sense to run those lines in parallel to at least cover the legacy equipment. But even in there, if you go through the economics and cost analysis, it makes more sense to then just locally convert DC into AC. And it also provides you with the added value that that AC is more reliable than what you would get from utility, because you can back it up with solar, with battery storage, with all sources providing energy to the DC microgrid as such.
Yeah, so this is a totally off-grid community, so I don't have that. The only AC I've got is this big generator, and we're going to have a problem. I mean, it's dark here. It's dark. It's winter. It rains all the time. We're flooded out here in Vancouver area. It's a disaster. We don't have a lot of option for generating power in the winter. So is there a more efficient way to generate DC power using, if you have to, using a fossil fuel? Is there a way to do that more efficiently than, you know, these great big diesel generator we run all the time?
Yeah, I'd say fuel cells are a way to generate DC power. If you have access to natural gas fuel cells would be something that we would look into seeing if it makes the sense adding it to projects where you don't have a lot of solar or wind generation, if you will, and you want that resilience, because at least in the US we have some of our natural gas pipelines running underground, so they can also provide added resiliency.
Yeah, so here we would have access to propane.
Or propane tank. Yeah, exactly.
Yeah. Okay.
Yeah.
All right. I'll let other people. I got lots of questions and I could talk all day, but I'll let somebody.
Yeah. So feel free to reach out to us.
Thank you.
Yeah, and thank you so much, Scott, because I think since you're so ahead of the curve, you're basically addressing problems we're all about to address. So we will circle back to other questions because they're really good too. Our next question is from Reed Rollins. Hi, Reed. Reed left the room. Hang on. I will ask Reed's question for him. I know he won't mind. I know Reed well. He said, when you say microgrid DC, how micro? One single family house, small commercial building, or only larger projects? He's looking for a question about scale.
Yeah, so I think the terminology in the industry is still evolving. Microgrids, nanogrids, picogrids, you know, we'll have that ironed out. And I know when you say microgrids in the AC world, you think almost like a utility scale. But really what we are talking about, we're talking about building scale microgrids. So for like commercial industrial buildings that have big flat rooftops that can support all this generation on the roof, building scale microgrids, right? The apartment complex can generate enough electricity to support itself. And then I guess community level, where you can support multiple homes on a smaller microgrid, you know, call it, you know, 6 to 20 homes or so. It depends really. So Giel?
Yeah, sure. That's I think the million-dollar question as well. When you're talking about microgrids, indeed, they're not defined in terms of size. But indeed, we're looking here at. I think we started with building level microgrids, and we're now actually working on the first handful of projects where also the community is involved. Because indeed it will start making a lot of sense. For instance, if you have rooftop solar generation, your neighbor wants to charge his or her car, that you actually then also use that DC infrastructure to get the power shared across the community. So yeah, we're more focused currently in terms of the projects on, let's say, community level, but yeah, who knows, in a couple of years, we're also talking about cities that maybe be a collection of microgrids at the building level. I personally, but that's more kind of opinion, have like that actually every building actually should be like have the capability to like island from the community. It should be grid connected in normal operating conditions, AC or DC grid connected, but having that level of independence will turn out to be a better choice to ensure that there's power quality in there. Because with all these millions of generators in there, I expect that there will be a lot of interactions happening. And if you can isolate them from one building to another, I think that will save a lot of troubles in there.
Thank you. That's a great answer. And Dusan, I remember when you presented at FIAS, you gave a good tip. So I'm going to ask this question and see if you can remember the one I'm talking about. But what can designers doing houses today do to prepare their projects for a DC grid or a DC system tomorrow? What can they do now to think ahead so that when they're building a new home, it will adapt easily?
Yeah, absolutely. So the way the homes are designed right now, we have AC and DC power distribution within the homes. But if you're building a community from the get-go, put some extra conduit in place and make sure that there's some wiring, piping available between the homes, because once you can do DC, just put some wires through those pipes and start connecting homes together and share those resources to make the community more resilient. Yeah.
Yes, you read my mind. Perfect. So I remember the first time someone said, even if they're not going to put solar on the roof, run conduit to the roof. And that way, when they do, it's already ready to go. It goes straight to the electrical panel. And now I'm not going to build another house without running conduit to each neighbor. So just like Giel said, you have that ability to island, to be independent, and then you have the ability to be interdependent, which is, still keeping it very local. And hey, it's like borrowing a cup of milk from your neighbor, right? You just a cup of milk, a cup of sugar, a little DC.
Hello.
Okay, well, our next question is from John.
AC that he has connected.
Oh, sorry, Derek. Go ahead, jump in.
Really related to this, which is great because it has to do with transition strategies, because that's one of the biggest issues and questions people have. And Dusan has a great example of the AC power regulators that we're using now. It's actually connecting them into the DC network, but they're primarily AC/DC regulators. So you can plug them in today to the AC network. Dusan, can you tell people about how that works, the mean wells?
Are you talking about the dual input power ones?
Yeah, just the mean well, the HEP 1000s and HEP 600s we're using.
So there's a dirty little secret with DC and AC power. You can generally feed DC into AC equipment because DC tends to bypass the rectification stage. So even if it's not designed to go to be DC out of the gate and eliminate all that extra e-waste, you can still feed DC into it. And more manufacturers are now dual certifying these products as well. But you can't feed AC into DC. Don't do that. That's not going to be good. So what Derek was mentioning, there's a Meanwhile makes a lot of power products, and so what power converters that generate 48 volt DC or 24 volt DC or 56 volt DC in output, and today you can plug AC into them and kind of run your little DC microgrid. And then in the future, if you decide to build a DC infrastructure where you unplug from the wall and you feed the new DC into it, so they're dual power input, which is really great.
Excellent. Well, our next question is from John. John, I know you had a few questions. Do you want to unmute and ask your first one?
Yeah. What DC voltage would you suggest using for distribution over 500 feet or so, 500, 600 feet? And what gauge wire?
Well, so the wire gauge depends really on the power level that you're going to run. Yeah. And 500-600 feet, we've used 380 volts DC before to do that. It's pretty efficient to to run. I mean, we use sometimes, 12 gauge wires to run 5 kilowatts of load, if you will. But that really depends on how much load you do, and then ohms law is easier on DC too. So then you figure out your wire gauges. Yeah, I'd say if you have like very power hungry equipment, you might want to consider higher voltage. But in the US, at least within the building for distribution, you can't exceed 600 volts, whether that's AC or DC, just because the wire's insulation rating as well.
This is external between houses, and each house has a couple of electric cars for charging them. So of course that's going to suck a lot of energy.
Oh yeah, you want to go high.
Yeah, I'm guessing 600 volts between the houses and the solar panels.
Yeah. So we'd like to create like a little standard. So we would recommend like 700 volts DC and kind of just standardize on that within the homes, and then just becomes easier. But yeah, exactly 600-700 volts.
Yeah. Tisha Lane had a related question. I don't know if you want to jump to her, Shannon. She just asked this a minute ago.
Yeah, I saw that. I usually like to keep people in order, John, but since it is related, I'm going to take you up on it. So, Tisha, if you are able to unmute and ask your question, please do.
Yeah, I actually have a lot of questions, and I think just clarifying some of the information you guys spread or presented would help clarify for a lot of other people and their questions. Like I'm noticing questions about the one that would just happen, differences between AC and DC generation, and just the general understanding that to generate AC is a wave. So when we generate AC, we use something that spins. That's where windmills, and you can use water. It can all generate AC because you end up hooking two wires to two sides of something, and as it's spinning, it'll make a wave. And then from that, you have to convert to DC, whereas DC is, I don't know of any place where it's really generated, it's stored, simply because it's just a flat line of current that you're getting when you have a load to it. So understanding those two principles, I'm assuming that leads to a lot of questions I have just on, and I'm sorry, I'm kind of going broad because there's little categories and I have a lot of notes. But are all of your microgrids based off of solar panels? And then that would answer a lot of people's questions on, how much power, because if I'm assuming it must have to be based on solar power or some kind of backup batteries. And then what do you have? How much load how much power can they source? And questions like that. And then I have this whole other side where, so I work in, I'm a controls engineer, and I design wiring systems for machines and in the plant. And there's a way that we do this. There's a way that it's now almost a lot of DC has came into the industry. I use DC for so much, but there's a lot of stuff where we still don't, it's just not efficient enough to use for higher torque motors, things like that. Now in residential, you don't really have a lot of these things. So I can see where you could take advantage of that. But then that leads to questions as in your DC home, what things are powered by DC? Do you have how are you drying your clothes in your stove? Are you using gas supplements, or is that where you start to use AC? Like where are your limitations to what your DC can supply? And that's a lot. So and back to the main question, I was just shooting off a bunch of them, because then we can get into the nitty gritties where I was asking about, what wire sizes are you using? You said you'd like to use 700 volts, or like you said, you capped at 600 volts, and small systems are less than 600 volts. DC servos that power robots, those are all 3-phase. They're AC motors, but they do convert to DC to be able to change frequency, like to play with creating a different frequency for the drives, and that controls speed and things like that. So there is
Tisha, let me hang on 1 second. Let's go back to your first question, because I really like where you're coming from, because you're dealing with a lot of the availability and a lot of the design from a specialized spot where you're doing and experiencing a lot of DC suddenly, right, in your life. So Dusan and Giel, can you talk about, are you always drawing from solar? And do you want to expand a little bit on some of the things Tisha was asking about?
Well, actually, yes, a primary source of energy indeed are solar panels generating a DC voltage. However, it's not the only one. For instance, in one of the projects that we showed, we also rely upon wind turbines, micro wind turbines in there. And indeed, although it's indeed a wave type of generation, because they operate at variable speeds, we're doing exactly the opposite thing as we're having with variable speed drives. It also requires a converter in between. Large wind turbines are out there as well. Actually, they have power electronics sitting in between because you need to be able to control the speed of all those things. And it's everywhere where you encounter control that actually power electronics are sitting in there, because those are the things that enable you to control. They are your actuators, so to speak, in there. And actually everywhere where you encounter that power electronic conversion step, except for a very limited amount of power conversion topologies, there's always an intermediate stage that uses DC in there. So not only solar, also other ones, but typically they are then power converter interfaced in there so that they anyway operate on DC. Then maybe Dusan, you want to add something or?
Well, I'd say the other sources of generation that we are evaluating are hydrogen fuel cells as well. Although they're not very efficient, they still have their place in some of these designs. Yeah.
Yeah.
And then maybe you can whoever was asking the question, you can ask your other questions.
That sounds great. I'm going to actually hold the rest of those and keep going down the list so that everybody gets a turn, and then I'm totally going to circle back. If you have to leave early, just private message me and I will try to fit you in beforehand. And if anybody has to leave early, the Passive House Accelerator Construction Tech website will have this presentation on the main site. I'm dropping a link in the chat right now. We'll have this recorded presentation up in 7 days. So if you have to go, you can come back and see all of the good information. Reach out to our presenters or just watch it again. Share it with your friends. So the next question up in chat is from Hans. Hans, would you like to unmute yourself?
Hey, thanks for this great presentation. I have a few questions, most of which have been answered, but is there a strategy of converting eventually to DC, or theoretically, if you had all the resources you needed, what would be your way to convert the grid to DC?
In my opinion, I think it's a kind of natural evolution that we're going through. If we're adding electric vehicles to the mix, and actually you combine it with solar generation, actually we're already running DC wiring through our houses, through our buildings as such. So I think because of the nature of these applications, actually DC will just naturally pop up. We also see that, like in the past 15 years ago, finding DC connectors in there was like a nightmare. Finding DC protective devices, it was a nightmare. Switchgear, the same things. Why do we have these things today? It's because actually the PV world has emerged since then. So they provided a lot of connectors in there. So I think DC is like a logical consequence as we're moving towards distributed generation and storage, as well as electric vehicle charging in there. So I don't think it's really a market push, it's just a natural consequence of where we're heading with our entire energy system. Besides, one more thing to add to that is that actually we're talking about increasing the level of electrification. So it's not about replacing the AC infrastructure, it's rather complementing it. It's adding an additional layer to that. For instance, I envision that will, for instance, for EV charging stations, we'll have like a DC infrastructure that's AC connected. We'll interface our solar in there, and we like gather all the more high power equipment at the DC level, but still make use of the current legacy AC infrastructure to power the loads we power today. Before we move towards like transitioning and making a complete overhaul of the system. It's more like AC and DC, especially in the transition phase.
Is it an inconvenience though for grid operators, or do they actually want to go that way?
Yeah, we have been talking to a lot of grid operators indeed in the past couple of years. They are definitely interested in DC technology because actually they can transfer more power across the same lines. So they, by means of the same amount of conductor material, they can basically deliver more power to consumers. So there's definitely a technical interest of system operators. However, the other side of the medal is that those operators typically would like to also standardize on equipment that they have, standardize on procedures. And of course, adding a technology there adds complexity into the assets they need to maintain and the procedures that go with it. So yes, interested technically, but in terms of putting it into practice, there's still a long way to go. But yeah, we're working with them to get them on that path, but we're not there yet for sure.
Thanks, that's super interesting.
Son, you mentioned, I might have missed it tonight, but during the dry run, you mentioned how much more energy a data center uses than a building. And did you do that tonight? Did I miss it?
I'm not sure we talked about data centers that may have in Giel, but
was it you, Giel? I'm sorry, I conflated your presentations.
Yeah, it's okay.
Can you remind me how much more energy a data center uses than a building? Because we're all so focused on saving energy at the building level in this group. And it was really eye-opening for me because it made me feel like I should just be designing data centers instead and making them more efficient. And so that's my first question. And then my second question is, if you could pick a typology to apply DC grids to in order to save the most amount of energy, what typology would that be?
Well, to elaborate more on the data centers, indeed, per square meter, so let's say 4 square feet approx, it's typically consuming like 5 to 10 megawatt hours on an annual basis. So that's almost equivalent to a regular household in there. So just 1 square meter in there. It's 1 server rack running continuously. So it's a huge drain of energy. And worldwide, data centers currently consume, if I still recall the right number, but I thought last time I checked it was about 2% worldwide. So it's almost like the entire Germany of electricity that's being consumed. And that number is expected to rise, although there are also like efficiency gains anticipated in that. So hopefully that will not rise just proportional with the use that will digitize our economy. So, but yeah, they're a huge consumer in there. And in terms of carbon emissions, even exceeding air travel currently. So yeah, definitely something to watch.
Wow. Yeah, that makes me want to hang up on everybody right now, even though I love you all dearly. We have got to do something about that. That is really staggering to hear. And I'm going to be thinking about that a lot all over again. Now we've got everyone thinking about it. Okay, so our next question is from Andreas in New York City. Andreas, would you like to unmute?
Yep, I'm unmuted. Hi there. Got a question on the practical implementation of a DC conversion for home. What type of wiring would you be using? Is it just the regular wiring that you're using already? How safe is it? You know, obviously, you know, there's always concerns about electrocuting yourself potentially. And is there like UL approvals for this kind of wiring yet? Are we going to jeopardize our home insurance because we might be setting it on fire if we use the wrong plug or something like that? I'm very interested actually in converting my own little cabin into that, but obviously, I want to know how to go about that and how feasible that is in today's world.
Sure. Well, I think converting commercial buildings are actually easier if you want to reuse the same wiring than residential homes. And simply because in a commercial building, more electrical codes let you isolate the neutral wire to a specific circuit. So let's say if you run your wires in a commercial building to lighting, there's nothing really else on existing neutral wires but that circuit. So I can take the AC lights off with DC ones on, and I can change the generation source DC and re-energize the same wires. In a home, that neutral wire carries other things sometimes too. So retrofits, I think, are very tricky, and we haven't touched those retrofits yet for that reason. But as far as regulations go, wires are approved for up to 600 volts DC. That's your limit there, and they can carry AC or DC current, so you don't have an issue. What you may need to consider if you do a retrofit are color coding. There's a National Electrical Code Article 712 that now specifically focuses on DC microgrids, and they kind of address the color coding. And you don't necessarily have to rip out all the electrical infrastructure if you retrofit just to adopt the color coding they call for, but you have to maybe take the white wire and put a red tape on it at every junction point that's accessible to an electrician. And then typically the authorities that have jurisdiction approve these systems. As far as safety goes, I love this topic because I think DC is safer than AC. And that's because with DC, we have access to various grounding configurations that help and limit the fault currents through a person's body to ground. So one grounding topology is a midpoint ground system. There literally are resistors between your lines and ground. And if a person touches it, the fault currents are limited to be less than whatever puts your heart into fibrillation. So, in a commercial facility, I would not touch 480 volts DC, but in a midpoint grounded system, if you touch it, it will hurt, but it will not kill you. And as far as resiliency goes with these grounding configurations, a single fault will let the system keep operating, and only a dual fault causes a short circuit condition. So it's even more resilient against faults, I would say. And then, yes, UL equipment is required to put inside these buildings. And so a lot of our effort goes right now to make sure that manufacturers provide UL certified equipment to these projects. So I always say that, the generation and distribution is relatively easy, but that last 10% when you're putting appliances into buildings and things like that, that's the hard part. And with the discussions we have with manufacturers, it's not that they don't want to produce DC variants of their products or they can't. They're just waiting for the market to catch up, kind of solve the chicken and egg problem, right? There's no DC systems, there's no DC products, there's no DC products for DC systems. But pretty much like Giel mentioned earlier, internally, all the high efficiency equipment has some kind of a drive, which is DC internally. And so manufacturers are ready to deploy these products. They just need a reason to do so. So it's still a lot of convincing today, but once that one big guy does it, everybody else will follow.
Then everyone's going to need your software, which
well, right.
I love the name, by the way. Okay, next question up from Eric. Eric Ram, would you like to unmute? Are you still here?
Hi, yeah, I'm still here. I came
Great.
back. I just wonder, let's see, with respect to, let's say, new residential construction or residential construction in general, is there a mini hierarchy of voltages within the home, in particular, from the point of view of safety? is there a concern of high DC voltages relative to AC voltages? Obviously at 24 to 48 volts, there's a little bit less. I mean, I've been known to stick a 9-volt battery on my tongue quite a few times in my life. So we all know that even, you know, enough current, it's current that makes a difference. But I just thought if you could mention any, you know, safety concerns.
Yeah, I'll let Giel chime in, but I think one thing I'd like to mention that may not be obvious is that when you connect to an electrical panel at home or in a commercial facility, there's, for all intents and purposes, unlimited amount of energy behind it. So a fault can cause a lot of arcing and a lot of damage, and that's why it's super dangerous. But when you're on these microgrids, your faults are limited in the amount of current and fault they can generate and contribute, the amount of power they can contribute to a fault. Solar panels can only put out so much energy, right? And batteries that are behind the converters can only put out so much fault current. So inherently, these systems are much safer because of that. And then, you know, there's a big popularity around 60 volts DC and lower. You'll see a lot of products being manufactured right now, especially in the lighting space and making fans and stuff, just because for two reasons, at least from my opinion. The efficacy of the products have increased, so we can effectively do more with less, just because everything increased in efficiency. And UL certification standards are less strict for 60 volts DC and below, as opposed to when you go 60 volts DC and higher. It requires a large investment to make those products safe and certified. Giel?
Yeah, indeed. The safety aspect, it's always it's a question we frequently encounter in there, also in the standardization committees. Actually, for instance, at IEC level, I'm taking part of those discussions in there. And when we're talking about safety, we should always be careful about what aspect of safety are we talking about. We're talking about preventing fire in houses by overloading conditions, short circuits, arcing. That's one aspect. And we have overcurrent protection for that. We have short circuit protection for that. So is there a risk that you short a circuit? Obviously, yes. Is there a risk you overload conditions? But that's why you put in protective devices, just as we're used to in AC today. So there's a risk, but we have protective measures that we can take. Secondly, you need to protect people against electrocution, basically, so that if they touch something, even if it's a metal part that should not be under voltage, actually they should be safe. And the first measure you always then take is like ground your system properly. That's the first thing. And there in DC, you have them freedom basically to adjust the grounding configuration to a particular condition, like Dusan already talked about, like having a high impedance grounded system, low impedance. I mean, you have complete freedom there. And depending on the grounding configuration, you again put in safety measures in place, like we do in AC. We put in GFDIs basically in there to detect ground fault currents, or we're putting isolation monitoring device to verify whether our system is still high impedance grounded. So is there a risk of electrocution like with overcurrent short circuits? Yes, but we can protect against it. And then one final note about voltages. Actually, the safe to touch voltage for DC is for just dry skin 120 volt in the IEC standards nowadays. That's higher than the 50 volt we define for AC. Why is that the case? Because actually the 50 and 60 hertz region also happens to be a resonance frequency of our heart, basically. So our heart will resonate to that frequency. So if we get shocked by that, actually it will more heavily respond to that, and the effect will be more severe. However, that just more a side note, because in my opinion, that kind of draws the attention away from the main aspect, because then we're talking about 50 volt, 120 volt max in DC. While actually here we're talking about distribution voltages going up to 700 volt DC, and they're, yeah, basically touching either AC at that level or DC at that level. You just need to make sure your protective devices take care that such a hazard no longer remains in the system. So you need to protect against it, whatever it takes, DC or AC.
Thank you so much for that question. I know a lot of people chimed in when you asked it and wanted to know the answer as well. So I'm going to ask Tisha to come back on and ask another one of her questions. Tisha, would you like to unmute?
Oh, sure. I got a lot. So I guess when we were talking, we were talking about, we got a little bit into to say if you were going to short to ground. So then that made me question, and then you explained how, like you can only get as much power as your source has. And with these DC systems, they're a little more limited. So what does happen, or how do you protect from somebody overloading the circuit and taking down the whole microgrid?
Ooh, good question.
Yeah. So that's where a control system comes in place, that we realized we also have to develop to monitor the system in real time, and making sure that the energy sources are always adequate enough to meet the demand. Because yes, when you plug a load inside your home, you can plug any kind of load and turn it on, and it will typically handle it because the utility will provide you that buffer. But if you have a limited power plant that's your own, and you plug something in and it's not managed, it can absolutely collapse the grid. So some management is required, and there are also, and I'll let Giel chime into this one, there's communication ways to handle it, and there's also what we call in the industry droop control based, and I'll let Giel talk about how that power is managed with droop.
Yeah, exactly. Overload conditions, just when everything is steadily operating, are obviously a concern, and then we're talking about managing the energy flows over there. So that's indeed where the control system comes into play. However, something also to watch out for in DC in terms of like overloading are inrush currents. Basically, when you connect a device to a DC bus, typically you have that a DC input capacitor sitting in there, and that DC input capacitor is 0 volts initially, so it presents actually a very brief short circuit current to the entire DC microgrid, causing a high short inrush current going towards the system that may, if you're not paying attention to it, blow up your fuses, cause protective devices to trip in there. So you need to take measures to actually gradually pre-charge your DC capacitors in there to prevent that overload conditioning from happening. As far as droop control considers, so actually for the audience that's not familiar with that concept, so basically within a DC microgrid, you need to have assets in place that take care of the voltage in there. So we're having systems that are capable of operating in islanding mode, but that also means that, of course, your control system should make sure that locally you make sure that your voltage is nicely smooth and stable at all times. And that's where droop control comes in. It's actually a control feature that you add to all the assets that are responsible for controlling the voltage into your system. And it's a control method that does not rely upon communication at all, but it, however, still allows you to have like multiple assets together controlling the same DC voltage. So they all see the same DC voltage, they respond to it, and without coordinating or communicating amongst each other, they actually make sure that your DC voltage remains stable. That's a very short explanation about how it works, but that proves out to be a very reliable manner because you don't require any communication at all. And when one asset, for instance, fails at controlling the voltage, another one can easily take over and your entire system remains online, and you prevent a single point of failure from occurring in there.
Yeah, so in short, fault tolerance and safety can be achieved by either high-speed communication and high-level management, or this droop control that's integrated in the devices.
And then that's a final comment I'll make on that. So indeed, there are also examples of DC pilots where they also use the voltage as a signal to basically signal to your loads and generators whether there's a condition of like oversupply or undersupply in the system. DC systems typically, like the voltage lowers when there's a lot of load, and the voltage rises when there's a lot of generation as compared to the load. So the voltage in itself carries a signal showing you like, is there a lot of generation available, or am I in a very heavily loaded condition? And that allows you to respond as a load to that voltage level. If you, for instance, let's consider LED lighting, you may say, if the voltage drops a little and I observe that the system is entering into a state of high loading conditions, I may say I'm gonna, as a preventive measure, like lower the intensity of the lighting a little, maybe even not really noticeable, but maybe 5 to 10%, lowering the lighting load by an equivalent amount. So you can respond to the voltage and use that signal to also have a very basic means of managing the energy flows and keeping the balance between load and generation at all times. I'm gonna leave it at that point now. Jen, back to
That
you.
is an amazing spot to leave it, because when I think about the difference between modeling for use and then the fluctuation of use, and then reporting and commissioning and
right,
and trying to use the data that's coming to kind of comment on the design is going to be even harder with respect to that, or we're really going to have to be specifying interactive way of monitoring, so that we can plug and play that into the model as we design. Maybe you can comment on how you see that going, but save that question, because really I'm jumping the line. Next is Consolidated Brick. Consolidated Brick, would you like to unmute if you're still here? Let me do a quick search. It looks like they are not. How about Derek? Derek, would you like to come on?
Hey there, I'm here. Yeah, thank you. I actually, Dusan and I work together quite a bit, so I don't have that many questions. I can say that, from the architects and engineers and builders that are starting to use these kinds of products and solutions, it really is I don't want to say it's commodity, but it's kind of there. Certainly, definitely on the lighting side, what I do is kind of commoditized DC. But what's really exciting to see is that the prevalence of these DC loads, and the fact that basically everything is internally a DC load, kind of shows that now you can start to bridge that gap of the building level. And if you're building any kind of a larger structure like the examples that Dusan gave, it becomes really palpable to look at the DC microgrid as an option because of the benefits that it provides with resiliency and energy savings. And there's so few steps that are needed to get us to that point. It's like Shannon's example of, put the conduit in for the rooftop solar, because it's there, right? It's just going to be there. All of this stuff is going to happen. And so, it's almost behooves us to not screw over our customers for the next 30 years by not putting in that tiny little bit of effort it takes to put these kinds of systems in. I'm sorry, Dusan, I didn't have any new questions for today.
Oh, that's okay. So yeah, so like Derek mentioned, we work quite a lot because Derek provides the low voltage 48-volt lighting system, which are kind of just like a no-brainer in these buildings. I think if I'm ever building a new home, I'm putting 48-volt DC lighting there. You get the flexibility and the resilience of a DC system, and you get your communications integrated.
Yeah,
it's amazing.
In fact, it was funny because the lab that you're in right now,
Yeah,
there was the panel that's on the wall there.
Yeah.
And I remember so clearly the first time you called me up and you powered it up and you were telling me about something called a black start.
Yeah, exactly.
Can you explain what that is? Because that was like the first time I had heard people describe it, because you deal with a much different level of power.
So when we design these communities that are self-sustaining, we make sure that they can black start. So that means that they can start from any source of generation that's available. And we always make sure that you can start your entire system from solar only. And this requires a lot of forethought when you try to implement the control systems, because you want to make sure that, you know, if your grid is dead and if your energy storage system is dead and if your fuel cells are dead, you at least want to be able to start from solar because it's available. Unlike with the traditional grid today, you have to disconnect if you can't island, but with the DC, solar is there. So then what do? You have to create like a hierarchy control system that says, all right, solar's powered up, you get your controls up, and then you start putting on your mission critical load slowly. And then depending on how much energy you have available, and if only solar you have, and if only lights you have, then that's great, because as long as the sun comes up, the lights come on. And then once more generation sources come online, then you can increase your addition of additional loads. But that's yeah, thanks for reminding me of that, because that's a unique and cool feature of these DC systems.
And yours in particular, I guess, handles that quite well, which is important.
Yes.
Cool. Thanks.
Thank you.
Well, it's almost that time tonight, and we do have some more questions in the queue, but it looks like we might have to answer those offline. So before we run out of time, I want to remind people that if you go to the chat and you hit those 3 little dots, you can save the chat. And when you hit save chat, it will say show in folder, and you can save that file right to your desktop or move it anywhere you like. And that way you'll get all the links that we shared. You'll also get a lot of the contact information for the presenters. And if you want to connect with them offline because you want the questions sooner than we can get it to you, please do. So with that, Dusan, Giel, what would you like to leave us with, knowing now that we've got some good practical tools in our belts thanks to your presentation? And also, I do want to ask, who was it? Let's see, it was Hans who wanted to know, what is the big box right next to the car in the back, and where is the lab?
You're talking about from like the background picture that you have, the big box? That's a styler from LG. It's like your own personal dry cleaner. These things are pretty popular in Korea, and so these are one of the first products that are being adapted to DC. You know, in the US they're about $1,700. Not sure where I would put it, but it's a thing. It's a steamer. Yeah. Refreshes your clothes.
I was not expecting that.
Yeah.
And where is the lab located?
In Charlotte, North Carolina. Yeah.
Excellent.
So yeah.
Yeah,
So yeah,
Shannon,
I just
understand I thought it was the car charger. You know,
I
that's what
know,
I thought
me
the
too.
box
I thought
was.
it was going to be something about
Kevin and I
the
were
car.
having bets of what it was, and we lost.
Well, now you know where you can get your suit pressed, Sean.
That's
exactly.
It. Hey, I'm coming your way, buddy.
The suit needs to be pressed once a year.
It's it. December 1st. Get it in the cycle. Here we go.
Sounds good. Yeah.
Kevin and Sean, any parting questions or comments before we wrap up an amazing presentation? Thank you guys so much for being here.
Yeah, the last 55 minutes here with questions have just flown through. And again, thank you guys for handling the questions really well. A lot of great insight what you guys are doing. And as you said in your presentation, the future is DC. And thanks for, again, leading us the way there. No, it's fantastic. So appreciate all the info, guys. And give a shout out for the man across the pond. I think he's at what, 2 a.m. Are we 3 a.m.? What time is it over there now?
It's now near 3 a.m. Yeah.
Oh,
wow.
More coffee.
Thank you for putting in the late night shift to bring us all your insights and info. It's great to see where you guys are at. And again, the takeaways too of your market opportunities when you're dealing with the, again, the Amazons and the Google databases is pretty insightful. But thanks for spending a little bit of time on making homes better too with your DC info. So lots of great stuff to take away from tonight. So thanks very much.
And
thank you for having us.
I
Yeah.
appreciate you.
Absolutely. And usually we go around the horn and we make people say the words over my shoulder on this side, and then the words over my shoulder on this side. But Dusan and Giel, I'm just going to ask you guys to do it tonight. Do you think you can pull this off together?
I think we can manage.
All right, on the count of three,
We'll
maybe.
try.
1, 2, 3.
Passive House Accelerator
construction tech. Technical technique.
Technical technology. We failed because when he speaks, the presentation goes small, and I'm like, where did it go?
I'm
the other
sure
way
these
around.
Christmas lights don't help, right? I think they might be obscuring the view.
I think we are better at designing microgrids than
Yeah.
repeating words.
We gave
Well-
it a try, Dusan. Let's get back to our regular business.
Yeah,
Right,
yeah.
don't quit your day job. Yes.
Not gonna quit
Well,
my day job.
we will be happy to have you back anytime that you can come. I hope you
Great.
both have a wonderful holiday, good night's rest. And I know, Dusan, you'll never sleep again because of the new baby, but good luck trying.
Thank you so much. Loving every minute of it. Thank you. And thank you for having us. It's been great.
Absolutely. And thank you to everybody else tonight for coming. Have a wonderful holiday. We will miss you, and we will see you next year.
Merry
Good
New
night,
Year.
everybody. Happy New Year.
Here. Thank you. Take care.
Bye. Thanks for having us.
Happy holidays.
New
Happy
year, new fun.
holidays.
Tech Tuesday coming in strong. 2022.
Woo!
Need lights on Sean's jacket next year.